We're used to shortages in the world of electronic engineering, right? There was that one time when Karen ate the last cupcake when Steve finally retired. Never thought that guy was actually going to leave. Or that one time when you were 4 hours deep into your last overnight project and the dude at the corner store ran out of Mountain Dew. I mean, yes, I had a cola, but you guys, it's really not even close to the same thing. And who runs out of dew in the first place? Must be a coding school or something nearby. All right, all kidding and snacks aside, there is a real honest shortage in the world of MLCCs these days. And folks, it ain't looking good for at least another couple of years. We've got to look for some sugary, caffeinated alternatives. Wait, I think I might be mixing up things here. Hi, I'm Amelia Dalton, host of Chalk Talk. You know it and I know it. More and more engineers are suffering from MLC long lead times. If you don't want your next design cycle to run into the next decade, we need to start looking at alternatives. In this episode of Chalk Talk, Rob O'Connor from Panasonic joins me to talk about Panasonic's capacitor technologies and the MLCC alternatives that will keep our design on track. And we'll still need to talk to Karen about that cupcake business. But that's a story for another day. And before we get started, don't forget to click that link. There you can find more information about Panasonic's capacitor technologies. Hey, Rob, thank you so much for joining me.
Hello.
So I've been hearing rumblings about an MLCC shortage for a while. So, Rob, how bad is this looking?
Well, I think a quote from an industry expert really says it all, that this problem is going to be so huge that it's going to last beyond 2020. It's much bigger than anybody knows right now.
Okay, so this is going to last until 2020? How bad will this get globally?
Well, the big problem is right now that in certain markets, especially in high reliability markets like automotive, the demand far outpaces the ability for manufacturers to increase their capacity. Also in very small, precise applications like smartphones and other consumer electronics, again, same problem. A lot greater demand than the ability for manufacturers to increase their production. The big problem is that there is a huge gap between the ability for suppliers to supply product and the actual demand, and it's not going to end anytime soon.
Okay, so what can someone do about this?
Panasonic has a program right now utilizing some alternatives to MLCCs to kind of rescue customers from their current situation.
So specifically, how can Panasonic help with this situation? If you guys no longer make MLCCs, what do you have to offer?
Panasonic has 4 different families of polymer capacitors and 1 surface mount film capacitor that actually can be utilized in a lot of MLCC applications as good alternatives, and in some cases actually have better performance.
So I know that a lot of MLCCs are for applications where you need extremely low ESR. What can we use in that case?
Well, in that case, Panasonic's SP-Cap polymer aluminum capacitors are a perfect choice. Being a pure polymer capacitor, they have ultra-low ESR. They are ideal for cases where you have high ripple currents in things such as DC to DC converters for FPGA applications or microprocessor applications.
Okay, so what if we need a larger capacitance?
In that case, Panasonic's POSCAP tantalum polymer capacitors are ideal. They give you the benefits of a tantalum capacitor having high capacity and also the benefits of a polymer capacitor having low ESR. So they're ideal, again, for digital circuits where capacitance is a requirement, but you also have high ripple current requirements as well.
Do you have anything bigger, say for higher capacitance?
Yes, we absolutely do. The OSCON Aluminum-Polymer capacitors offer, again, very low ESR, but because of their size, they also offer very high capacitance, up to 2700 microfarads, as well as having high voltage capability up to 100 volts.
Okay, wait a minute. Rob, what about safety? What about applications where safety is really important?
That's a question that comes up very often because polymer capacitors, unfortunately, have a short circuit failure mode. In the case of Panasonic, they're very benign, but in some cases that's kind of unacceptable. So in that case, if you need a very, very benign failure mode, that's where the Panasonic hybrid capacitor comes in. It gives you the benefits of a polymer capacitor, again, having very low ESR, very high ripple current, but its failure mode is very, very benign. It fails just like an aluminum electrolytic in an open circuit.
So where do all these capacitors fit in circuit?
Well, Panasonic's polymer capacitors, depending on the family type, fit in different parts of a typical circuit. So on the high voltage side, that's where an OSCON or a hybrid would fit, in voltages up to 100 volts. It's a place where you need high capacitance and very low ripple current, and that's where they fit best. When you go on to the next level of voltage regulation, that's where SP caps and POS caps fit in. Again, voltages you're typically seeing are anywhere up to 24 volts. And again, your ripple current is very high, and you begin to have issues with size. So those fit in perfectly there. When you get to the point of load regulators for an ASIC or an FPGA or a microprocessor, it's again where SP cap and POS cap fit in perfectly. You typically have extremely high ripple currents and very low voltage, and they fit perfectly there.
Okay, so Rob, you're telling me that these parts are better, but how do they match up with MLCCs, really?
Well, that's one of the places where polymer capacitor technology shines, especially in the area of temperature and DC bias characteristics. Polymer capacitors overall have very stable characteristics. When you look at the temperature characteristic, it barely changes over its entire operating temperature, where typical X5R and X7R really go all over the map. It's something that engineers often fail to recognize and plan for until they have a problem. DC bias is something I've gotten questions about over and over again, where people think they have more capacitance than they actually do. Higher the DC bias voltages, the lower the capacitance. So customers think that they have a 100 microfarad cap, and in reality, they have something much, much lower.
So how do these polymers perform over time?
Again, that's another area where polymer capacitors shine, because really from the point that you solder them down to the board to the point of what we consider end of life, polymer capacitors' characteristics really don't change very much. On the other hand, with MLCCs, you typically see a DC bias change, but then over time as they age, the capacitance begins to drift down and gets lower and lower. And that's something, again, you have to plan for. You really need to know, where is this part going to be at the end of my product's life? And that's something that you can count on with a polymer capacitor.
Okay, so can you give me some examples of these alternatives?
Sure. So I have a quick example for you. On the input side of a typical DC to DC converter, you can see maybe 3 25 volt, 22 microfarad X5R capacitors. And on first look, it looks like 66 microfarads, but once you take into account the DC bias, there truly are about 19.5 microfarad capacitor. You can easily replace that with one SP cap rated at 25 volts and 22 microfarads. What you end up in the end is about 60% smaller PC board space requirements. On the output, you might be using 600 microfarad 6.3 volt X5R capacitors. And again, if you look at the capacitance with 0 volts of bias, that's 600 microfarads. But with the 5 volt bias, it's only 150 microfarads. So it can again easily be replaced with one 6.3 volt 150 microfarad SP cap, saving you a whopping 70%.
So Rob, do you have any direct examples?
So I have a couple of quick examples for you at different bias voltages and also 2 different case sizes, because not only does bias voltage change things, but also case size has an impact as well. In this case, we have a 5 volt, a 15 volt, and a 25 volt example. And you can see in a 1210 package, you actually need less capacitors than a 1206. And ultimately, all you need is one SP cap for each of these examples.
All right, let's dive into some details. Can we look at that first one, the 5 volt?
In our first example at 5 volts, you'd end up needing 3 6.3 volt 47 microfarad capacitors in a 1210 package, which at 0 volts have a capacitance of 141 microfarads, but once you add in the 5 volt DC bias, only have an effective capacitance of 109.9 microfarads. If you move to a smaller package, say the 1206 package, you'd need 5 pieces of a 6.3 volt 47 microfarad capacitor. At 0 volts, they have a capacitance of 235 microfarads, but when you add in the DC bias, it's only 108.1 microfarads, as compared to an SP cap, which you only need one part, 6.3 volt 100 microfarad part, which doesn't matter whether you have a 0 volt DC bias on it or a 5 volt DC bias on it, it's still a 100 microfarad part. If you take a quick look at the chart, you can see what we're talking about here, that the higher the DC bias, the lower the effective capacitance is. And unfortunately, when you move into a smaller package, the problem is exacerbated. And you're going to see that with my further examples. It gets worse the higher the applied DC voltage. And with the SP cap, and it's true of the other polymer capacitors, it doesn't matter if you apply 0 volts to it or its full rated voltage, the capacitance remains stable.
Okay, let's move on over to the next example, I believe was 15 volt?
Sure, in our next example with a 15 volt rail, the problem gets a little worse. In a 1210 package, you would need 4 25 volt, 22 microfarad capacitors, which would end up giving you at 0 volts, again, 88 microfarads, but with a 15 volt bias on it, you're down to 30.8 microfarads. With a smaller package, the 1206, you now need 8 pieces of a 25 volt, 22 microfarad capacitor, which at 0 volts has 176 microfarad capacitance, but with that DC bias of 15 volts, it's only 31.6 microfarads. And with the SP cap again, 16 volt part, 33 microfarads at 15 volts is still a 33 microfarad part. And if we take a quick look at the graphs, you can see how much worse the graphs are as we move to 15 volts.
And finally, what about 25 volt?
Unfortunately, at 25 volts, the problem gets even worse. So you end up needing to move up to a higher voltage MLCC, which doesn't help you with your DC bias problem. So you end up needing 4 pieces of 50 volt, 10 microfarad part with a 0 volt capacitance of 40 microfarads, but at 25 volts, it's only 24.8 microfarads. In a 1206 package, you now need 12 pieces of that same value, 50 volt, 10 microfarad with a 0 volt capacitance of 120 microfarads, but only 21.6 microfarads at 25 volts. And as you can see, again, the SP cap, nothing changes. 35 volt, 22 microfarad part at 25 volts is still 22 microfarads. And when you look at the curves get worse. And it will continue on as a DC bias gets higher and higher. That problem gets worse and worse, and you need even more MLCCs to have the same effective capacitance.
Now, what about analog applications? Do you guys have anything that could help me there?
We sure do. Panasonic offers surface mount film capacitors, which have extremely stable characteristics and tight tolerances, low ESR, but the big deal is that it has low dissipation factor, no shock noise, and especially important for analog applications, no piezoelectric effect.
Now, how does this one compare to MLCC?
Yes, surface mount film capacitors, similar to polymers, have extremely stable temperature characteristic, but even more important for analog circuits, surface mount film capacitors have extremely stable frequency characteristics.
So where would these be used in an analog circuit?
Well, they can be used all over in a typical analog circuit, but especially in places like decoupling caps, caps that are used as part of filter networks, stabilization caps for voltage references, and they can also be used anywhere else that a low capacitance part is needed. And the nice thing about surface mount film capacitors is in some cases they might be drop-in replacements for MLCCs.
MLCCs are obviously used just about everywhere, but I understand that these polymer alternatives have safety advantages?
That's very true. MLCCs are right now, as I say, the workhorse of the electronic industry, but there's some definite drawbacks, and safety being one of them. Unfortunately, the failure mode of an MLCC is a short circuit, and that short circuit can end up being pretty spectacular. In the case of both of our surface mount polymer families, while they fail in a short circuit mode, their short circuit mode is pretty benign. They sit there, they'll smolder a little bit, but nothing as spectacular as an MLCC.
Okay, Rob, what else should I be keeping in mind as I look for MLCC alternatives?
The first thing that has to be taken into account is the fact that, with exception of film capacitors, these are not drop-in replacements. They really require some design, not only changes in the PC board, but really you need to understand what you're trying to accomplish with your design. So you have to take into account operating voltage, the required capacitance, ripple current, operating frequency, also mechanical things like the maximum allowable height. MLCCs obviously being very compact parts, and in some cases, some of the capacitors that we're suggesting can be quite tall. Also, what is your total solution cost? We believe in most cases you'll probably have somewhat of a savings, but if you're only using a handful of MLCCs, there's things that need to be considered there. And lastly, manufacturing issues have to be taken into account. MLCCs are virtually indestructible, and polymer capacitors need a little bit more care. Manufacturing engineering needs to be involved and understand that things probably need to be adjusted for these different capacitor technologies.
Okay, fantastic. Now, where should I go for more information?
That's a great question. The best thing to do is visit our website, where we have additional resources, white papers, and other information, and an ability to actually get a little extra help if needed.
Well, I think that's all I have time for today. Thank you so much for joining me, Rob.
It was my pleasure.
And before we go, you didn't forget to click that link, did you? There you can find more information about Panasonic capacitor technologies. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, check out the Chalk Talk section of EE Journal. Can't miss it, right across the top. Or head on over to YouTube. Keyword EE Journal.